All right, so the first of two examples here. Water in a river approaches a 5.7 meter drop. So just to give you a sketch, water coming down, goes down a waterfall, continues on. So the water is something like that. So we know the velocity at the top here is about 5.1 meters per second. So just reading ahead. I know the drop is 5.7. I don't know why I picked funny numbers for the example. We want to know for each kilogram of water, A, what's the total energy at the top of the falls? Well, total energy, ET, is equal to EG plus EK plus E mechanical plus ... So all the energies that are involved. Now in this one, again, we're at sort of the beginning stage. We're in introductory material. So here there's only two energies that are involved. Gravitational potential and your kinetic energy. Gravitational potential, so mgh plus 1/2 mv squared. So we're looking at 1 kilogram of water, 9.81. Gravitational potential, or the height, sorry, is 5.7 plus 1/2, 1 kilogram of water, and it's traveling at 5.1 meters per second squared. So there we go. There is the total energy at the top of the waterfall. So you have kinetic energy, it's already moving, plus that drop, that potential energy. So we're using the bottom altitude, or this is our reference line. So this is our reference for GPE. Okay. So 9.81 times the 5.7 plus half of 5.1 squared equals, so 60, let's call it 69 joules per kilogram. So therefore, each kilogram of water has 69 joules of energy. So B part. What's the total energy at the bottom of the waterfall? So how much energy does the water have once it falls? The answer here, same thing. ET equals 69 joules. It's the total energy for the system. So the water doesn't lose it. What happens is it's converted to kinetic energy. So therefore, each kilogram still has 69 joules of energy. Okay. Now C part. What's the velocity prior to impact? So ET again, total energy equals EG plus EK. Those are the only two that were involved in this one, so I'm going to leave, not going to add the other ones in. 69 is the total energy at the bottom. At the bottom, the height is 0, so maybe I'll go one more step here. MGH plus 1/2 mv squared. Because the height is 0, that means that the MGH drops out completely. So that means that at the bottom, 69 joules is all kinetic energy. So now we can calculate the velocity of the falling water by solving for V. So we end up with 69 divided by 0.5, take the square root, and now the velocity of the water is 11.7 meters per second. So therefore, velocity of water is now 11.7 meters per second. Okay, so that total energy is constant throughout, based on a physics world. All right, and that's what we're going to assume for this, for the both grade 11 and grade 12 courses. And because of that, it allows us to make those calculations at the start and the end. So the next example, the final example here, it really exemplifies that. So student shoots an arrow straight up at 30 meters per second. So obviously you're not paying attention during your archery class, and you're going to do something silly, and you're going to shoot the arrow straight up. The arrow has a mass of 0.04 kilograms. Answer the following. What's the maximum height of the arrow? So remember that total energy, ET equals EK plus EG plus etc. etc. We can figure out how much energy was given to the arrow at the start. So that's all kinetic energy when it's on the ground. Okay, so 1/2 mv squared. So 1/2, the arrow was 0.04 kilograms, and it was given 30 meters per second from its velocity. So at the very bottom, at the ground level, the arrow has no potential energy. It's all kinetic. Okay, and I guess in some ways maybe I should just note that. So ET equals EK plus 0. And just as a note, EG equals 0 joules at a height of 0 meters, just for note purposes here. So the 0.5 times 0.04 times 30 squared. So that means this arrow has 18 joules of energy. So that means that when you fire it upward, what happens? Well, it's kinetic energy. Actually, why don't I show a graph? This is a little bit better. So let's look at it graphically here. All right. On this axis, let's put height in meters. No, that's not going to work real well there. Let's go with height on the x-axis. That's a little bit backwards. It's what you're going to be normally used to, but it makes sense here. So height is 0, and then I'm just going to go max because I don't know what the max height is yet. So how much energy is in this system? Well, it's 18 joules. Does it matter where? Absolutely not. So the energy, total energy, is ET. It's always 18. At 0 meters high, our gravitational energy is 0. When it gets to a maximum height, then its energy is maxed. So our EG, my line in green, is going to look like that. My kinetic energy, it's maximized at a height of 0, but when it stops moving, when it reaches that maximum height in the parabola, if you're to follow it parabolically, when it reaches that vertex, we said in an earlier unit, the velocity vertical is 0 meters per second. If that's the case, then it has no energy there. So we end up with that pattern there. So that's my kinetic energy. So therefore, to finish this A part, this original part of the question here, then we find out that E total equals mgh. So the total is 18. My mass is 0.04. Gravity, 9.81. And my height, so isolating for height, we get 18 divided by 0.04 times 9.81 in brackets, 45.9 meters. So therefore, max height would be 45.9 meters. So that arrow is going to go upward 45.9 meters. B part. If the gym ceiling is 15 meters high, what velocity will the arrow strike the ceiling? We always fall back to our conservation of energy formula here. EK plus EG, or whatever order you want it in. Total energy for this whole system is always 18 joules. EK is going to be 1/2 mv squared plus mgh. So we're looking for velocity, so that should mean we know all the other pieces of information here. So I know the mass, 0.04. I'm looking for velocity, so that's all right. 0.04 again for mass, 9.81. And we're looking at the height of the ceiling, it's 15 meters. So what is the impact velocity? How hard or what velocity will the arrow strike the ceiling here? So doing a little bit of math, we got 0.5 times 0.04, so 0.02 v squared plus the 0.04, oops, times 9.81 times 15. We get 5, let's call it 5.9. Moving the 5.9 over, so 18 minus 5.9, I get 12.1 equals 0.02 v squared. Don't forget the velocity is squared, so you are going to have to take the square root in the end here. So 605 equals v squared, square root. V equals 24.6 meters per second. Is that reasonable? It was launched at 30, so it has lost some velocity. So therefore, it makes sense. So therefore, impact velocity is 24.6 meters per second. There we are. So here's the homework. I would recommend making sure to start with the handout, actually. I would leave the textbook stuff alone and go straight to the handout. A little bit more comprehensive, a little bit more challenging. If you're really concerned, you can start with the homework in the textbook, but the handout, I think, kind of gets you going conceptually a little bit more. So there we are. No, this is actually, if I was teaching this in class, this would have been a 2-day lesson. So it may take you 2 days to get homework complete in class. So don't be too frustrated if it does take that length of time. I try to point out when it should take a little extra time. But I would say this is a 2-day homework session coming up here for you. So any questions, make sure you ask and I'll get them clarified for you. Good luck.